In Chapter 5, we discuss Newton's third law. This is the law of action-reaction. For every force, there's an equal and opposite force. And we'll learn about it in detail. Let's look at a couple examples like the tennis racket here. When you hit a tennis ball, of course the tennis ball has a force applied to it. But what's less obvious, maybe, is that exactly the same moment that the ball feels the force, the tennis racket feels an opposite force, and we see the distortion of the tennis racket as proof of that. Yoda said, the force is between you, me, and everything else. There's no such thing as a force in isolation. Forces are always an interaction between two objects. I want to remind you that at the end of every chapter, there are review questions which will help solidify your understanding based on the reading. In fact, at the end of every chapter, there are some reading comprehension type questions. You do those first to make sure that you understand the material before you start into the problems, like the mastering physics problems. Okay, so we'll talk about Newton's third law, forces and interactions, how forces work. We'll state it more formally as the law of motion, and then we'll briefly summarize Newton's three laws: the inertia law, Newton's second law, and the action-reaction law. If you push against your hand, then both hands are being pushed together. If you push on the wall, is the wall pushing back on your hand? It is. You can check that it is because look at the flesh on your fingers. When you push against the wall or push against a table, your fingers get pushed in. When you push on the wall always pushes back. And that's just a simple everyday example of Newton's third law. The example of pushing on the wall and the wall pushes back gives us evidence that there's no such thing as just a one-way force. In other words, forces always come in pairs. An interaction is a pair of forces. And all forces act that way. Now, a boxer might be able to punch with like 100 pounds of force. But when a boxer punches a piece of paper, the force is always tiny. Why is that? We'll have to discuss that. We'll talk about it in when we meet in lecture in person. But let's think about that. Why is it impossible for the boxer to punch the paper with 100 pounds of force? Let's now put down the third law in a more formal, precise way. It says this: whenever object A exerts a force on object B, then object B exerts an equal but opposite force on A. Remember that forces have directions. So A pushes on B in some direction, B pushes on A with exactly the same magnitude of force, like 100. If it's 100 pounds on B, then it's 100 pounds on A, and the directions are just opposite. A pushes B one way, B pushes on A the opposite way. We call it the law of action-reaction, but be careful because the term can be a little bit confusing. Action-reaction makes it sound like action and then reaction. In fact, they are simultaneous. It's not that one occurs and then the other. They're instantaneous at the exact same moment. That's how the action-reaction works. They are simultaneous. There's no such thing as a delayed reaction when it comes to forces. Okay, for instance, a bowling ball hits a pin, and we know that when the ball hits the pin, there's a force that's applied to the pin. Pin feels a force. That's the force on the pin. What Newton's third law says is that for every action, meaning for every force on an object, there's an equal but opposite reaction force that occurs simultaneously. In other words, the instant the pin feels the force, the ball feels an exact opposite but equal force. There's a force on the ball that's exactly equal strength. And that's the law of action-reaction. Now, when the ball hits the pin, it's tempting to say the reaction is the pin goes flying, but that's not how the terms are used here. Okay? Action-reaction refers to the pair of forces that occur instantaneously when they hit. Okay? The fact that the pin goes flying off, which of Newton's laws is that? Okay, so this action-reaction, they're simultaneous forces. Neither force exists without the other. If one of them's there, the other one's there immediately at the exact same instant. Okay, the forces act on a pair of objects. Crucial to remember that. If the action force acts on one object, the reaction never acts on the same object. It's always on another object. It's between a pair of objects. For example, when you hammer something in, hammer hits a nail. What's the reaction force to the hammer hitting the nail? Well, we don't like to nail things by hand. The reason is the force that you give to the nail gives an equal but opposite force upon your hand. So the reaction force is the nail hits the hammer. And that's why I don't nail things by hand. That's why I don't hammer things by hand, because whatever force you give, you get back on you. How did Newton figure out this law? Because it's not obvious. Is it obvious that when one football player tackles another, that they feel the same force on them? No, it's tempting to think that maybe the person running faster gives more force on the impact or something like that. But it's just not true. The way he figured it out is by studying pendulums as they collide against each other. And what he noticed is when the blue ball hits the yellow comes off with a certain speed and the blue with the same speed, and the blue ball stops. It indicates that the force which hit the yellow ball is exactly the same force which stopped the blue ball. And that's how he came up with the third law of motion. Okay, some examples. First, let's look at these. Why is this an example of the third law? Well, the dog jumps forwards. In fact, the dog is pushed forwards by the friction on the paddleboard. But if the dog is pushed forwards, the paddleboard is pushed backwards, and that's action-reaction. Swimming is an example of action-reaction. You are pushed forwards by the water. And how do you do that? You push the water backwards. Action-reaction. Okay. A car drive. What makes a car go? Well, the engine has to run, of course, but the engine just turns the wheels. And what actually drives the car is friction. You see, the tire pushes back on the road. And the reaction is the road pushes the tires forwards. So it's actually the force of friction which pushes on the car and makes the car move forward. It's a great example of action-reaction. A rocket. A rocket can fly out in empty space. A rocket doesn't have to push on any kind of atmosphere around it to move. How's that possible? A car has to push off the ground to drive. What does a rocket push off of? Well, a rocket pushes on the gas that it ejects out the back, the burning fuel, and that gas is what pushes the rocket forward. So it's self-contained. It doesn't have to push off an external thing exactly. It pushes the gas backwards, the gas pushes the rocket forwards. A helicopter works a similar way. Helicopter blades spin. They push the air downwards, right? They blow air downwards like a fan. And if you push air down, then the helicopter is pushed upwards. It's like swimming in the air. Push air down, you get pushed up. Man pulls on the spring, The reaction is the spring pulls on the man. If you pull in that spring, you're going to feel the spring pulling back on you. Notice how the action and reaction always works. You just switch the subject and the object of the sentence. Man pulls on spring pulls on man. Here's one that's trickier. Earth pulls on the ball. You drop the ball, and I know that Earth's gravity pulls it downwards. Earth pulls on the ball. What's the reaction to that? And what in the world does it mean? Think about that one for a while. We'll come back to that one in lecture. More examples. If you get mad and you punch the wall, it might hurt you. If your fist hits the wall, then guess what? The wall hits your fist with an equal force. If you head a soccer ball, then your head bumps the ball, but of course the ball also bumps your head and you feel that. Bug splatters on the windshield. The windshield hits the bug. What's the reaction? Bug hits the windshield. In fact, the bug hits the windshield with the same force that the windshield hits the bug. Why does the bug splatter then? Come back to that. A soccer player kicks a ball with 1,500 newtons of force. The ball exerts a reaction force against the player's foot of somewhat less than, equal to 1,500, or somewhat more than 1,500. Or is it somehow none of the above? Pause it, think about it for a minute. Well, this is an example of action-reaction. Foot kicks the ball. The reaction is ball kicks the foot with an exactly equal but opposite force. However hard you kick that ball, the ball kicks you back. That's how forces operate. A bus collides with a bug. The force of impact splatters the bug. Which is greater, the force on the bug or the force on the bus? Would you believe that it's both the same? It's the same on both. Now, how can that be? How can it be that the force is the same on the bug as on the bus windshield, but it's the bug that splatters? More everyday examples. Bat hits the ball, but sometimes the bat shatters. That's the ball hitting the bat. That's the reaction. Hand touches nose, but the nose touches your hand. You can feel that on your fingertip. Pulling weeds. If a hand pulls on a flower, then doesn't the flower pull back on you? Sure. There's an action-reaction. Sometimes it's really stuck and you're pulling on it, might pull you down, you might fall over. All good everyday examples of action-reaction. Here's one. Lifting weights. An athlete pushes the bar upwards. Doesn't the athlete feel a push downwards as well? Of course. And that's what makes it so difficult. There's a reaction to the upward push. Compressed air pushes the balloon surface outwards. What's the reaction to that? Well, the balloon is rubber, and that surface pushes the air inwards, compresses it. Surface pushes in. And in fact, the air inside of the balloon is squeezed by the rubber on the balloon. Cook up your own example here. There are millions of everyday examples of action-reaction, where you push on something and it pushes you back. I push on a door, the door pushes on me. Come up with your own. Is the Force in Star Wars an example that obeys the third law? Well, all forces are supposed to. If Vader squeezes on somebody, he should feel equal force pushing back on him. Does he in the films? I don't know, but that's how the third law actually works. Slightly tilted wings of airplanes. Do they deflect the air downwards to produce lift or upwards to produce lift? Is it both or neither? I'm going to answer that one when we come to lecture. And we talked about what moves your car. The tires push back against the road, and the road pushes the car forwards. And if it's rainy outside, you know that. If there's no friction on the roadway, no traction, no friction, then you can't drive. Your wheels just spin in place. If the wheels can't push back on the ground because it's too slippery, then the ground can't push your car forwards. There's a famous kind of paradox or puzzle which comes out of the third law, which it's kind of a joke or a puzzle where the horse complains to the driver, I can't pull that cart because if I pull the cart forwards, it pulls back on me. We can't move anywhere. And so the horse just gives up. Said a different way, the puzzle's this. How's motion possible? For every force, there's an equal but opposite force. So doesn't everything just cancel out and nothing ever happens? Okay. The answer to this is no. Motion is certainly possible. I can stand up and walk away right now if I wanted to. How is it possible for every force there's an opposite force? The answer is it hinges on the fact that the action-reaction forces are on different objects. Action, reaction. They act on two different objects. Okay. So for example, in this picture, the apple pulls the orange. And remember how tension works. The apple is holding a rope. Remember how tension works. When you pull on a rope, the ends of the rope pull inwards. Okay. So we see the evidence of the equal but opposite forces here. By means of the rope, the apple pulls the orange forwards. That's the force which makes the orange move. Okay, there's no puzzle here. What force makes the orange go? It's that one that I just circled. Now, there is a backwards reaction force which acts the other way. But notice how that force does not act on the orange, right? There's the action force that acts on the orange, and there's the reaction, but the reaction isn't opposing the action force. It's actually pulling the apple backwards, okay? So we can easily solve this puzzle of how motion's possible by just deciding what system to look at. So the system is indicated here. If I want to know how it's possible to move the orange, let me isolate the orange from everything else and say that's my system that I'm going to study and understand how it moves. So how can the orange move? Well, there's a force pulling the orange forwards, so it'll move. That's actually the second law. F equals ma. If there's a force on the orange will accelerate forwards. Okay, there we go. So here it is, just drawn in isolation. There's an external force that acts on the orange. External force on the orange causes its acceleration. No paradox, no puzzle at all. Simple as that. The acceleration of the orange would be equal to the force that the apple gives, F, divided by the mass of the orange and the cart that it's riding in. Now, what about the system as a whole? Because then, the apple might complain, okay, well, there's a backward force on me. So what if we take the system being apple and orange together? Then what? Now what force makes the system go? Well, now you got to look at all the forces that act on this whole system. So there is a force pulling the orange forwards. There's a backwards force on the apple. Now that I take the entire system together, those do cancel out. However, those aren't the only forces in play here. You can't ignore the fact that there is friction on the ground, this one here. The apple gets traction on the ground, and that friction force is what actually moves the system forwards. Okay, there's no paradox. There's always an unbalanced force which allows motion to happen. That's how we walk. You can't claim, oh, I can't walk because if I push back on the ground, then there's an equal force forwards and they all cancel. Well, they don't cancel because if you want to know how you walk, you realize that there is just the reaction force of friction pushing on your feet forwards. Sure, there's a backwards force on the ground. That's not a force on you. It's a force backwards on the ground that you're stepping on. Same with what makes a car go. The tire pushes back on the road. The road pushes forwards on the car. You don't cancel them out because they're on different objects. When you kick a ball, the ball feels the same force that you feel. There's no paradox here. The forces act on different things. Your foot gets slowed down by the impact. The ball goes flying off. Poor Coyote can never catch the Roadrunner, not because he gets screwed over by the laws of physics, but because whenever he tries to do something, for him, the laws of physics break down temporarily. What was wrong about that video is that the cannon recoiled, but the Coyote didn't go flying out. That's impossible. We know that for every force, there's an equal and opposite force. If the cannon gets pushed backwards, then the Coyote has to get pushed forwards. Okay, so an actual cannon will recoil. And when a cannon is fired, in fact, the accelerations of the cannon and cannonball are different. Why is it that if the forces are the same, apparently the accelerations are not? The cannonball goes flying out with a large acceleration. The cannon itself does have some acceleration backwards, but it's not as big. Is it because the forces don't occur at the same time? Is it because, although they're theoretically the same force, in practice they're not? Is it because the masses are different? Or because the ratios of force to mass are the same? Here's the situation. The cannonball and the cannon feel exactly the same force. At least if you're not in the Wile E. Coyote universe, they feel exactly the same force, the cannonball and the cannon. The difference is the cannonball has a relatively small mass compared to the cannon itself, which is very, very massive. So you see, if something's very massive, then it can take a lot of force without getting much acceleration. The rule you remember is that the acceleration of the cannon is going to be small because although it feels a large force, it's a tremendous mass. It can take a lot of force without getting much acceleration. Versus the cannonball is going to have a large acceleration because although it feels the same force as the cannon does, it has a relatively small mass. Same force divided by a tiny mass gives you a large acceleration, and that's what happens to the cannonball. So the reason that the accelerations are different is simply because their masses are different. Same force, but different acceleration. Newton figured out his 3 laws of motion. He built upon the ideas of Galileo. I want to review now what those laws of motion are. They're universal laws that apply all throughout the universe. The first law is the inertial law. The inertial law says that an object will continue in its motion. It doesn't require any force to do that. More precisely, the total amount of force, if the total amount of force on an object is 0, then it will just maintain a constant velocity. That is, it'll just keep its direction and speed. It goes the other way. If you ever see something just cruising along, maintaining its direction and speed, then you know there must be no force on it. But if it changes directions or its speed changes, then there has to be some force. Here, for example, we see this giant yacht coming in. It's a great example of inertia. Without any force to slow it down, it just continues its motion and crashes. The second law is about what happens, well, if there is an unbalanced force on an object. And it says you take the total amount of force that acts on an object, and that's equal to the mass times acceleration. Or to say it another way, the acceleration an object experiences is the total force that acts on it divided by its mass. An example of that is like hitting a ball, here hitting a golf ball. At first, the golf ball is in equilibrium. There are forces on it. There's the upward force from the pin and the downward force of the ball's weight. But as soon as the driver hits it, now there's a force acting to the right. In addition to those two, there's now an unbalanced force to the right, and it accelerates. The third law that we just discussed here in Chapter 5, that's our action-reaction law. And it says, if object A applies a force to B, then B applies an equal but opposite force onto object A. That's the action-reaction law. And we gave lots and lots of examples of this. One is still shown here. The driver hits the ball, but you see the ball also gives an equal force back to the driver. And it does slow down the driver a little bit. In any kind of collision, the force on object B is equal to the force back on object A. That's how all collisions work. And in fact, it was studying collisions that led Newton to the discovery of the third law. When the man pushes on the ball, he feels an equal force backwards. He will recoil backwards, just like a cannon. In the Coyote cartoons, the physics is all wrong. But Simpsons gets all the physics right. Bart recoils due to the fire extinguisher being sprayed forwards. He feels an equal force backwards and recoils. Simpsons get it all right. They've gotten everything right from smartwatches to the election of Trump. So of course they're going to get their physics right as well.